Just like in groups we saw the first, second and third isomorphism theorems, similarly the same thing applies to rings as well. So let's look at the first isomorphism theorem of rings. Now, if f is a function which maps R to S, where R and S are rings, then f is a ring homomorphism. Then there is a unique isomorphism G which maps R by kernel of f, or R mod kernel of f, to the image of f, okay, such that G of R plus kernel of f is equal to f of R. Okay, so what this basically means is that we have a ring where f maps it to image of f, which is a subset of S, and we have a mapping, say H, from R to R by kernel of f. Then the theorem says that there is a isomorphism G from R mod kernel of f to image of f. Okay, so let's prove this. So remember, we have to prove this G is a isomorphism. But as part of the proof, let's begin by saying that there is a function which maps R mod kernel of f to image of f. So we don't know whether it actually maps or not. So which means we have to check for well-definedness. Okay, so this G of R plus kernel of f is equal to f of R. Okay, so let's first check out whether it is well defined. Now let's say we have R plus kernel of f is equal to R prime plus kernel of f, where R and R prime belong to R. Now what this implies is that if we rearrange, we get R minus R prime belongs to kernel of f, or R prime minus R belongs to kernel of f. Okay, now let's apply the G function. So G of R plus kernel of f is equal to f of R. Now which is equal to, this can be written as f of R plus 0 of the image. Okay, so image of f, which is equal to f of R plus, now 0 prime can be written as f of R prime minus R, and this can be combined by saying f of R plus R prime minus R. So R and minus R get cancelled. So we end up with f of R prime. Now f of R prime can be written as f of R plus kernel of f. So what do we end up with? We end up with G of R plus kernel of f is equal to f of R plus kernel of f. So therefore it is well defined. Okay, now let's prove that G forms a ring homomorphism. Okay, so G of A plus kernel of f plus B plus kernel of f is equal to G of, we can rewrite this as G of A plus B plus kernel of f, which can be written as f of A plus B, which is equal to, again we can split this, f of A plus f of b. And this f of a can be written as g of a plus kernel of f, and f of b can be written as g of b plus kernel of f. So we have g of a plus kernel of f plus b plus kernel of f is equal to this. Now that we have done with respect to addition. Now we have to do the same thing with respect to multiplication. So g of a plus kernel of f times b plus kernel of f. Now let's see. This can be written as g of a times b plus kernel of f, and this can be written as f of a times b. This can be split into f of a times f of b, which f of a can be replaced with g of a plus kernel of f times f of b will be g of b plus kernel of f. So again, we have satisfied the condition for a ring homomorphism, both with respect to addition and with respect to multiplication. Now here remember, a plus kernel of f and b plus kernel of f belong to R mod kernel of f. G of a plus kernel of f and g of b plus kernel of f belongs to image of f. Okay. So we have shown that it is a ring homomorphism. The next thing we have to show is that it is one-to-one or injective. Okay. Now we know the condition that if kernel is trivial, then one-to-one. Let R plus kernel of f belong to kernel of G. If it belongs to kernel of G, that means G of R plus kernel of f is equal to 0 of G. Okay, 0 of the image of f, which implies that f of R is equal to 0 prime, which implies that R belongs to kernel of R plus kernel of f is equal to 0 plus kernel of f, which further implies that kernel of G is equal to 0 plus kernel of f. So therefore, kernel of G is trivial, which implies that G is injective. Now we have shown that it is well defined, that it is a ring homomorphism and it is one-to-one. Now we have to show that it is onto or subjective. This is pretty straightforward. F of R belongs to image of f. Let's apply G. So G of R plus kernel of f is equal to f of R, which belongs to the image of f, which implies that G of R plus kernel of f belongs to image of f. So therefore, it is onto. To show uniqueness, again pretty straightforward. Let's say we have G of R plus kernel of f is equal to f of R. Now let G prime be another function which also maps R plus kernel of f to f of R. Now, so G prime of R plus kernel of f is equal to G of R plus kernel of F. So which implies they are operating on the same element and they both are equal. So that means G prime is equal to G. So therefore unique. So that is the first isomorphism theorem of rings. That's it for now. Bye.